Astrofísica de La Plata in Argentina. And today I'm going to present some preliminary results we have obtained together with my supervisor, Romina Di Sisto, in modeling impact cratering in the Plutonian system. So as a brief introduction, the Plutonian system was studied up close in 2015 by the New Horizons mission that was able to obtain a large amount of data, especially, well, the smaller satellites, and especially for this topic today, for Pluto and Charon, because it obtained a lot of images with very high resolutions. This is very interesting for our work. So the first step in modeling impact cratering is, as I have presented in previous talks, modeling your impactor population. So in our model, our main impactor population are the heliocentric centaurs, which are originated mainly in the scattered disk. So in 2020, we performed a simulation that follows the dynamical evolution of the scattered disk objects as they migrate inwards into the solar system. And because we included Pluto as a massive object in the simulation, we were able to compute the encounters of the centaurs with Pluto. So then we combine these encounters to obtain the number of collisions of centaurs with each Plutonian object or each of the Plutonian system. We combine this with an impactor size frequency distribution that, as we can see here, we model it with a power law that has a break for impactors of 100 kilometers. And we combine this as well with crater scaling laws that relate the size of the impactor to the size of the crater. With all this, we can obtain the theoretical crater distributions, and in addition, we can fit a temporal function to the impact cratering process that allows us to obtain, if there are crater data, we can obtain the surface age for each region. And for the case of smaller satellites, we can also obtain the catastrophic disruption time, if there are catastrophic collisions. So all this is possible due to the observed crater distribution. So as always, I thank all the crater mappers for all the work you do, because it's essential for our work. A brief comment I wanted to make about the impactor size frequency distribution is that, as I mentioned, we have a break at 100 kilometers, but for the smaller objects, due to the uncertainty, we use two slopes, 3 and 3.5. And another brief comment I wanted to make about the crater scaling laws is that these vary between authors. We use this one that has a term for the gravity, the importance of gravity in the impact event, and another term that has the importance of the strength of the target in the impact event. And depending on the size of the object you're studying, this term can be important, as we will see later. So for this work, we used the crater data from the works of Kelsey Singer and collaborators from 2019, and the work by Stuart Robinson Singer from 2021. In these works, the authors analyzed different regions of Pluto and Charon, analyzing images with varying resolutions, as we can see here. And what the authors found is that across different regions, the distribution of the craters has a more steep distribution for the larger craters and a shallower distribution for the smaller craters. In this sense, we already use a steep slope for the larger craters, but we extend that steep slope into smaller craters. But I wanted to mention that the slopes they obtain are, in some cases, consistent with the 3.5, for example, slope that we have been using. So going into the results, the preliminary results we have obtained for Pluto in this work from Kelsey Singer and collaborators, we can see here the different regions that the authors analyzed, and here we can see our results. So this is the accumulated number of craters per square kilometer in terms of the size of the crater. And in black, we can see both our results for the two slopes that we consider below the break of 100 kilometers. And here in color, we can see the crater data with the vertical lines indicating the completeness limit. So what we are seeing here is what we have obtained in other systems as well, such as the Saturnian system, is that the larger craters on the more densely cratered areas are matched with our 3.5 model. So in this case, that would be the Cthulhu region, or I think now it's called Belton region. And as we have obtained as well in the Saturnian system, we can see that for the smaller craters, we tend to overestimate the number of craters. That we usually in the past were associating this with the fact that many smaller craters may be obliterated faster. So for this other data set for the same work, we can find similar results. Again, we can predict the larger craters, but overestimate a large number of craters here for the smaller craters. And comparing to the data from Robinson-Singer from 2021, again, similar results, except for this large crater, and an overestimation for the smaller craters. When we move to Sharon, we see here that the authors analyzed two different regions, where we have in the northern part the Ostera region that we see here in purple. And again, we are trying to always trying to predict the larger craters. So here we can see that the 3.5 model matches again, and the 3 model, as in the previous case, does not predict the craters. It underestimates the number of observed craters, both in both regions. So except for this crater, we can see that the 3.5 is returning good results. And in the case of the Vulcan Planitia here, when we have these kind of results where our model tends to overestimate the number of craters across all crater sizes, we can say that maybe Vulcan Planitia is, as a whole, a younger region. So it may have been resurfaced early in the history of Sharon, and that is why it lost the initial craters. And what we can see here again is that there is a larger overestimation for the smaller craters, and the same in the Robinson-Singer from 2021 dataset. So what we wanted to see in this preliminary work was if we can implement or introduce this proposed break into the impactor population. So in this case, what we would need is to propose the slope here, so a distribution for the impactors that are smaller than 1-2 kilometers is what the authors observed, and to translate this slope that is for the crater distribution into a slope of the impactor population. So this is done using the crater scaling laws that, as I mentioned before, because it has two terms, we have to be careful here because depending on the strength of the target you use and the density of the target, because Sharon is, for example, Sharon is not that large, this may be the transition from a gravity regime impact to a strength regime impact is around the proposed break for the crater distribution, is close. So it depends, of course, on the parameters you use for the surface. So in this case, because it's a preliminary results, you can use this if this is the strength regime, or this is the gravity regime. We use directly this one. So here in this plot, you can see our results considering a new slope in a new break or elbow for objects smaller than 1 kilometer, using 1.7 or 1.9 as it is plotted here. And as you can see, this is very interesting results because it virtually drops our expected number of craters for the smaller craters down to an overestimation that is consistent across different crater sizes, which is very interesting. So this is what we have obtained so far. That is why it is preliminary. We always have to check everything, of course. But I wanted to mention that it's very interesting, this break, and we have been wanting to implement it for a long time now. So as a conclusion and discussion of this work and future work, we are seeing that it may be important to keep on studying what is this possible new elbow or break in the impactor distribution. And of course, explore additional impactor populations of the Plutonian system, apart from the scattered disk objects. It could be Plutinos, for example. And of course, to fit the temporal function, as we have done with the Saturnian, Uranian, and Neptunian system for the craterinization process, that will allow us to quantify this difference and obtain, for example, surface age and the satellite age for the cases of the smaller satellites that may have been disrupted across the solar system age. So that's it. Thank you.
Let's all go out again.
Thank you. I saw you.
So we have, thank you, Natalia. We have 2.5 minutes for any questions, and for some reason I don't see anything in the chat. So if anyone in the chat would like to ask questions or raise your hand, or if anyone in the room has any questions, speak up